to some very basic concepts around artificial intelligence. Did anyone here read Ian Goodfellow's book on deep learning? It's a very, very popular book for those who want to learn deep learning. Ian Goodfellow. I had that in a picture here. Let me see if I can find. Oh yeah, this one. This book. It's a very, very popular book. There's also a new book by an author that I like, Christopher Bishop. That's also a book on deep learning. He wrote it with his son, I believe. That's also a very nice book. Machine learning. There are probably hundreds and hundreds of books online, and in print as well. Have you? I know you've taken a course on machine learning with applications, right? Has anyone here taken courses on machine learning? No? Okay. So for the vast majority, then my material is going to be new, which is good, and I hope you'll derive something new from what we're going to cover in the next few days. Okay. All right. I just wanted to show you this this slide. Is there anyone here who reads articles by Thomas Friedman in New York Times? He's an opinion columnist. He also writes lots of books. I really like some of his work. I think a few years ago, maybe now 10, 15 years ago, he wrote a book called The World is Flat, where he was arguing that we are innovating at an ever-increasing pace. And I think that proved to be prescient, because now, 10, 15 years later, after he wrote that book, we are seeing exactly that. And if you look at this plot here, you will see that handwriting recognition, it's something that I used to use many years ago, 15, 20 years ago. And those softwares used to be really bad, right? But they were available, people were marketing them. Unless you have really good handwriting, they were not good at recognizing handwriting. So you see this red, is that red? Yeah, so the red or purple line here, that shows the development in the algorithms used for handwriting recognition. In perhaps 1995 or so, they were nowhere near the human performance level. Right? And over the years, people started fine-tuning and those algorithms, and perhaps developing new algorithms. And you see that these errors started becoming better and better and better. 2012, somewhere over here, is when the deep learning idea was introduced. And after that, you see that these algorithms have now become much better than humans. Okay? Speech recognition, the same thing. The initial improvement in these algorithms was rather slow, and then 2012, deep learning comes out. Suddenly, you see a huge improvement in speech recognition algorithms as well. So image recognition, same pattern. 2012 was the inflection point. You suddenly see these algorithms becoming much better than human performance. Reading comprehension, much better than human performance. Language understanding, large language models, much better than human performance. Now, the interesting thing that you can observe between these curves is that the pace of innovation is accelerating. You look at handwriting recognition, it took us nearly 20 years for those algorithms to reach human-level performance. Speech recognition, almost 20 years. Image recognition, only about 6 or 7 years. Language understanding, much, much faster, right, to get to human-level performance. So that sort of indicates that the pace of innovation is really accelerating because of the tools that we have right now. I can give you a couple of other examples. Last year, I think it was last year, there was a study done at MIT where they were trying to develop new antibiotics. You've probably heard of this. Antibiotics are the current antibiotics that we have. They are the bacteria are becoming resistant to existing antibiotics, right? For nearly 60 or 70 years, similar, more or less the same chemical composition was used to manufacture different types of antibiotics. Last year, scientists at MIT, they did in silico simulations, meaning they design different types of molecules, they simulate them, they study their antibacterial properties. You can do that any number of times, right? You can do that millions of times. You can study millions of different types of molecules. And then you can identify the most promising candidates, use them to do experiments, and then design new antibiotics. That's the process they took. And they actually identified an entirely new class of antibiotics that nobody has ever known before using these machine learning tools, right? So I'm giving you that example because the pace of innovation is going to continue to accelerate, where we are likely to solve the most pressing societal problems, whether they are in health or climate change or energy or something else. With the tools that we're going to learn in the next 4 days, you'll have a better shot at solving some of these problems. Okay. Not just that, data scientists are in high demand. The jobs for data scientists are growing. So if you have these tools at your fingertips, I think you'll be in high demand in the workforce. All right. Now, some of you have heard of artificial intelligence or have taken courses in artificial intelligence. Can somebody here, I have a definition here, but can you define what artificial intelligence is, or what do you think is artificial intelligence? When somebody says artificial intelligence, what comes to your mind?
Human-like intelligence in machines.
Human-like intelligence in machines. Okay. And you, Surendra, you had something. Okay. Yeah. So, what about you? Sorry. Yeah. What's? No, that's okay. I have a chair here, so I can just. Yes, sir. To the extent possible, right? Yeah. I mean, you'll find many different variants of this. I think Alan Turing, who is considered one of the great scientists of 20th century, he said something like, why not? Why do you want to train an agent that works like a human? Instead, why not take an agent that behaves like a child and then feed it more data and it learns like a child, right? Or something of that type. But there's this quote from Minsky from 1968 that I like, and he says AI, artificial intelligence, is the science of making machines do things that require intelligence if done by people. Okay? Now, artificial intelligence is used in many, many different fields, in knowledge and inference to emulate expert decisions and expert behavior. It's used in problem solving to find solutions automatically for problems like packing problems or design tasks. Some of the things that ChatGPT can do is simply mind-boggling, right? So it can solve problems. How many of you here have used ChatGPT? I'd expect almost everyone, right? And I don't know if you know this statistic. Facebook took many years to have millions of users. ChatGPT took something like 3 months to get to 100 million users. It's probably the fastest, the growth of users that we've witnessed in any other product out there. Right? And I'm bringing that up because it can solve a lot of problems. Right? You can give it a mathematical problem and it will solve it. You can, I was able to get it to solve some very complex math problems. I have a colleague in the math department who teaches first-year engineering math course, and ChatGPT was able to solve almost every problem in their assignment, right? So you can use these tools to solve problems. You can also do state and action planning, to find a good or optimal sequence of actions to reach a predefined goal. That's what we do in reinforcement learning, and I'll get to reinforcement learning in a couple of days. So you can take optimal decisions under significant uncertainty using these tools. Natural language processing, you're all familiar with those examples. You can do natural language processing very effectively. Now you can learn probabilities. I'm not going to be delving into that topic, learning probabilities. Machine perception, you can deduce real-world aspects by using sensor input information, which is precisely what self-driving cars are doing. Machine learning. Machine learning is a subset of artificial intelligence. Often machine learning and artificial intelligence are used interchangeably, but that's not quite accurate. There is a subtle difference between artificial intelligence and machine learning, and I'm going to get to that in just a couple of slides. Actually, not a couple of slides. Next slide. So what is machine learning and what is artificial intelligence? I have taken some of these pictures from Ian Goodfellow's book, which is, by the way, an excellent textbook if you want to get started on deep learning. The entire textbook, I believe, is available online. So you can just search for Ian Goodfellow, Deep Learning. The textbook is completely, all of it is available online. So, Ian Goodfellow, let me go back to this. This one. Ian Goodfellow and Yoshua Bengio. Yeah, Ian Goodfellow. All right. Does anyone know the difference between machine learning and artificial intelligence? Right, but what's the difference? I mean, what subset of artificial intelligence is machine learning? Mm-hmm. Mm-hmm. Any other? Yes, go ahead. Mm-hmm. Right. Okay. Well, these are overlapping sets, right? So machine learning, everything that's machine learning is also artificial intelligence, right? But not all artificial intelligence algorithms are considered machine learning. And I think the difference, the way I understand it, is artificial intelligence as a phrase has been used since 1950s or so. And during that time, scientists have tried to imitate human behavior through a wide range of algorithms. And a lot of those algorithms are based on logic, right? So for instance, they would create a program that will do this if this is true, or do that if that something else is true, right? So it's sort of logic-based, but it would function like humans to do a certain task. And those are not, there's no optimization involved. You just create some logic and you get your program to execute that logic in the way that a human would do, right? So that's how artificial intelligence really started. And then over a period of many decades, scientists have been able to formulate more rigorous mathematical optimization problems to achieve similar results, sometimes better results than logic-based code, right? So that area where you have a mathematically rigorous optimization-based algorithm is called machine learning. So typically, most machine learning algorithms have some sort of optimization involved in them. Okay. So that's a subset. Artificial intelligence, for instance, knowledge bases. You create a knowledge base of data, and then you create some sort of a logic to extract information out of it. That would be considered an artificial intelligence algorithm. On the other hand, if you have a machine learning algorithm, say for instance logistic regression, you have some inputs, some outputs. You can use a logistic function to relate those inputs and outputs. Okay, and that is, in order to find that logistic function, you have to solve an optimization problem. So then that becomes a machine learning algorithm. So within machine learning, very early on, let's say you're training a neural network or you're building some other model. Often what used to happen was you would take your raw measurements and then transform them in order to get a better model, right? So you would manually design or transform your data for improving the quality of your models. As an example, if if you have a reactor, you have some temperature measurements, etc., and you're trying to build a model, often logarithm of the exponent of temperature would function as a better proxy for the original measurement, which is temperature, or some other functional form of your measurements would function better in terms of building your models. Has anyone here observed that? I mean, instead of taking your raw measurements, if you perform a transformation of the measurements, then you will likely get a better model. Okay, you'll find it in different engineering disciplines. If you use the original data, original measurement, you may or may not be able to fit your data really well. But if you make a logarithmic transformation and then fit the data, you sometimes get much better results. In other words, you have some raw data. Okay, so those are in machine learning language, they're called features. You have some raw data, and then you transform the data using some logarithmic functions or trigonometric functions or some other functions, and then you build a model, right? So instead of just taking your raw data, say raw data, okay, and then building some sort of a model, okay, for predictions. I'm going to typically use X for inputs and Y for outputs. Okay, so that's going to be my notation. If I use a hat, it means it's a prediction. If I don't use a hat, it's the real data. Okay. So you can do this, but often what happens is you take this raw data, you then transform it, and then you build a model. Okay. So that this model, if you know how to find these transformations, is going to be better. And I have a very simple example from Ian Goodfellow's book that will illustrate why this transformation is useful sometimes when you build these models. Okay. So a subset of machine learning algorithms are what are called representation learning. Algorithms where you try to find these transformations or representations. Okay, so that's what's called representation learning. And a subset of representation learning is deep learning. Now, if you know how to transform, how to find these representations, then you can get a better model. But what if you don't know how to find these transformations, how to find these representations? Then what are you going to do? It's not easy, right? What you can do is use deep learning to learn these transformations or representations, where You provide with deep learning, you provide raw data directly to your deep learning algorithm to get these predictions. So that's the difference between different types of machine learning. Raw machine learning, you're trying to go from the raw data to the model, but that's not very efficient always. So what people have done in the past is to transform the raw data and then build a model that's going to be better. Deep learning allows you to automatically find those unknown hidden transformations or representations. Okay. And because it's trying to find these hidden transformations or representations automatically, deep learning also often requires a significant amount of data to train. Are there any questions? Well, I'll get a bit more deeper into these topics. But if you have any questions, pass me. Sorry. Typically, in the past, we used to handcraft these transformations or representations. Yeah. Is also done automatically. So we're not doing anything by hand, right? There's no manual design of these representations. Instead, deep learning with its layers, you have multiple layers, a lot more layers in deep neural networks. Through those layers, you hope to learn these transformations or representations automatically. Right. Okay. If you look at the history of the development of artificial intelligence, there are many different ways in which we can talk about the history, but I think there are three major or key breakthroughs in artificial intelligence. That's what we're going to talk about in this course. And those three are statistical machine learning, deep neural networks, and reinforcement learning. Now, I'm trying to recall who, but somebody was asking me, when did you, or maybe it was you, Surendra, you were asking me, how long did it take you to learn machine learning, right? And I said, we've been doing statistical machine learning for a long time. It's just that we did not call it statistical machine learning. Has anyone here taken online courses by Andrew Ng at Stanford? Yeah, did you take it? Yeah. Yeah. Okay, yeah. He has a number of really nice courses on Coursera. If you get a chance, do take them because he delves much deeper into the algorithms that are behind machine learning. Artificial. It is quite mathematical. So it depends on, sorry? You got lost in it. Okay, so maybe that's not for everyone, right? It depends. As I said earlier this morning, if your goal is to do research, fundamental research in artificial intelligence, then you should watch all of those videos. But if your goal is to be able to identify machine learning problems, formulate machine learning problems, pick the right tool to solve those machine learning problems, then you don't have to go so deep under the hood, right? You have to understand what type of problems are out there, what type of tools are out there to solve, and maybe a little bit about the algorithms, because you do have to fine-tune certain hyperparameters when you use those algorithms, right? So if you don't know what those hyperparameters are, then you might run into problems in using those algorithms. So you have to be a little bit careful. But his courses are really nice, and I've watched them myself many years ago. I brought it up because in the very first course, I think he says least squares is a machine learning algorithm, right? That's where he starts. And all of us, I mean, many of you, I'm sure Surendra and I, we've all used least squares for many years. We just did not call it machine learning. But now it's fashionable to call some of those things machine learning. So we have in process control, which is where my expertise is, we have used statistical machine learning algorithms for many years. I mean, these include things like least squares, logistic regression, principal component analysis, partial least squares. A lot of those algorithms we've used for many decades. And I would say Statistical machine learning is classical machine learning. There are a couple of books that I can recommend that are excellent in this area. Both are written by Rob Tibshirani and Trevor Hasty. Rob Tibshirani and Trevor Hasty. Those books are, I think they're titled Statistical Learning with Applications in R or something like that. But if you search for Trevor Hasty and Rob Tibshirani, you'll find their books. So I think I'm going to talk about each of these breakthroughs. Statistical machine learning, which includes all these classical machine learning algorithms. I will scratch the surface of deep neural networks. I think Mithun is going to talk about deep neural networks in much more detail later in this workshop. And then I will also talk about reinforcement learning. I don't think anybody else is talking about reinforcement learning, so I will spend some time explaining what reinforcement learning is and also showing you some real applications. Okay, so let's start with statistical machine learning. So do some of you know supervised and unsupervised machine learning? Okay, so would you like to tell us what you know about supervised and unsupervised machine learning? Right, yeah, excellent. Good. Right, yeah. So let me draw a picture here for you. Can I erase? Oh, okay. Thank you. Thank you. So in supervised learning, models are trained using known inputs and outputs. So machine learning, if you read machine learning literature, inputs are often called features and outputs are often called labels. Okay, so I'm going to use those two terms interchangeably. So inputs are features and outputs are also called labels. Okay. So there are two primary types of problems that we solve in machine learning. One where we know only the inputs. We don't know the outputs. An example, can one of you give me an example of unsupervised learning? So if you only use inputs and you have to build a model, then that's called unsupervised learning. If you use both inputs and outputs to build your model, then that is supervised learning. Right? Can you think of examples of supervised and unsupervised learning? Sorry? Stock market prediction. Why is it? What's your input, or what are the features, and what are the outputs or labels? There are no labels because if you think it's unsupervised. All right, yeah. Okay. Right. Okay, yeah. I mean, I think that's a good example. So you know both the inputs as well as the outputs. So that's an example of supervised learning. Yeah. I see. Right, right. Okay, yeah. I think, image processing, we can go back to the ImageNet example that I mentioned this morning and generate a couple of unsupervised and supervised examples. So did someone here have an example? Sorry, what predictions? I see. Okay. Yeah, that's a possible example. So let me explain this using the ImageNet example, right? So in the ImageNet classification problem, there are 14 million images. Only some of them are labeled. The others are not labeled, right? Now you can create an unsupervised problem as follows. So you have approximately 12 million images that are not labeled, right? Now you can create a model that takes these 12 million images and puts them in different classes, different clusters. Let's say there are images of dogs in it. So your model will automatically identify all of those images, put them in one bucket. And then there are images of cats, and it'll automatically cluster them together because those images are similar, right? So that is unsupervised learning. You're only giving it images. You're not telling your algorithm what is in those images, right? You can also build a supervised model with those same images, but then to build a supervised model, you not only need those images, but you also need someone to label those images. So each image has to be labeled. If it has a cat, you have to label it as an image with a cat, right, or a dog, or whatever, or some other object, a bus, a car, etc. So you have to manually label those images and then create both the inputs and the outputs. Okay, so you then build your model to predict outputs for new inputs. Okay, so in supervised learning, once you build your model, what you do is you give a new input. This could be a new image to the model, and the model generates a new output. Okay, it'll tell you based on the labels, or based on the previous combination of inputs and outputs that were used in training the model. It'll tell you for any new input what the corresponding label or the output of the image is. Okay, does it make sense? If you are to do unsupervised learning on the same set of images because you don't have a label, when you give it a new input, so when you build your model basically, when you give it a new input, it will tell you if it belongs to some cluster 1 or 2 or 3 or 4, etc. So that's all it will tell you. It doesn't have labels, right? Hopefully, your model is good enough to put all cats in one cluster, dogs in another cluster, and so on, other objects, buses, cars, etc. Right? So when you give it a new input, it automatically figures out to what cluster it belongs to. So that's unsupervised learning. Okay. You probably have spam filters in your email, right? Some of those spam filters have unsupervised models. Sometimes, some email clients, I don't know if the ones that you use have this feature, but they ask you to label emails as junk if you think they're junk, right? So that sort of labeling helps whatever algorithm is running behind the scenes to improve the model and get those labels to work much, much better. Okay. So you can do both the unsupervised learning and supervised learning in sorting your email into legitimate email and spam email. if you think about it, there are only, I would say, 3 or 4 different types of problems you can solve in machine learning. You just have to, when you have an engineering problem, you have to figure out under what category that particular problem falls, and then you're done, right? So a large majority of problems are either supervised or unsupervised. Once you know what your problem is, the next step is going to be to identify the right tool to solve that problem. Right? There are lots of tools already in Python, MATLAB, etc. Applying the tool is not that difficult. Okay. So machine learning broadly can be classified into supervised learning and unsupervised learning. In supervised learning, we not only have features, but also labels that come with the data. In unsupervised learning, we just have features, but there are no associated labels. Okay. There are 2 big ideas behind supervised learning. One is classification, the other is regression. And we're going to talk about both of those approaches perhaps tomorrow. Unsupervised learning, the primary approach is what is called clustering. So you have some data, you have to identify data that are similar to each other. Classification, in classification and regression, you need the labels, not just the features or the inputs, but also the outputs or the labels in supervised learning. Okay. Yeah. No, they're not. They're not the same. Okay, so they're not same. Clustering, because you're trying. There are no labels, right? When you find clusters. So let me take an example here. I have different. Okay, so I have 2 colors here. So let's say you have some data. Okay, so X. 2-dimensional data. And some data points are blue, and some are black. Okay? There are 2 types of data in your data set. Some are blue, some are black. In clustering, you give this data to your clustering algorithm. You don't tell the algorithm which ones are blue and which ones are black. You don't tell that to the algorithm. So the algorithm is blind to the color of the data. You just give all of this data to your algorithm and ask it to find similarities between the data. And then your hope is that it would tell you that there is this cluster where all of those data look similar in some sense. They're all blue. And then there is this other cluster where all the data look similar and they're black. Okay, so that's clustering. You're not telling, when you do unsupervised learning or clustering, you don't tell the algorithm that there are black and blue data points. You don't tell it. It has to figure out automatically that there are black and blue data points. Yeah. Generally, yeah, they tend to be clustering problems, yeah. In classification, what we do is we tell the algorithm that these are the blue data points, okay, and these are the black data points. The algorithm knows that there are two classes, blue and black. That's it, right? So you tell it that there are this many clusters, and you expect the model to predict to which cluster any new point belongs to. Okay, in clustering, I may have confused clustering and classification. Clustering is an unsupervised learning algorithm where there are no labels. Classification is a supervised algorithm where you have labels, right? So if you do clustering, for instance, I only have blue and black data points. When you're given the data, you don't know how many clusters are in your data. It's anybody's guess, right? Because nobody has given you the labels. So if I give you the labels blue and black, then you know there are only two classes in your data. But if I don't give you the labels, then you don't know from the perspective of the algorithm, all are same data. There's no difference. Then often what you have to do is decide how many clusters you want to see in your data. So you specify that a priori. We're going to learn some of these algorithms a little later, but if you think there are three clusters in the data, even though there are only two different types of points, you might end up with one cluster here, one here, and one there, right? Because you don't have the labels and you don't know what these data are in reality, right? So that's the number of clusters that you choose in building these models is a hyperparameter. So you decide how many clusters you think there are. There are ways in which you can choose those automatically, but typically you decide how many clusters you think they are, or how many clusters you want to separate your data into. Did that answer your question? Yeah. Okay. Any other questions? No? Okay. Now you'll see that under each of these problems, classification, regression, and clustering, you'll notice that there are many, many algorithms to solve these problems, right? So if you take classification, support vector machines, discriminant analysis, Bayes methods, nearest neighbor, etc. There are lots of methods for classification problems. There are also, similarly, many different methods for regression, linear regression, SVR, GPR, ensemble methods, decision trees, etc. Clustering, again, there are many methods, k-means, C-means, fuzzy C-means, hierarchical, Gaussian mixtures, hidden Markov models, etc. There are many different ways or many different algorithms that you can use to solve these problems. Okay. But you'll notice that at the bottom, I've used neural networks under each of these classes of problems. You can solve classification problems using neural networks. You can solve regression problems using neural networks. You can solve clustering problems using neural networks. Okay. And now with deep learning and lots of data, you can essentially have a single algorithm solve all of these machine learning problems. Right? So you don't have to pick and choose. I have a very interesting plot that I picked from Andrew Ng's course on the performance of these algorithms compared to neural networks and why deep neural networks appear to perform far better than some of these algorithms. Any questions? So you want me to pause here for a second? Yeah. I mean, that's a good question, right? So I don't think deep learning is the answer to every problem, even though it can solve some of these problems. In fact, we published a paper a few years ago where we tried a wide range of deep learning tools on a certain problem. This is a problem that was released as a benchmark problem a couple of years ago. It's called the R-class problem. I think I have that problem in the later slides, and I will explain it to you. What we found there was, this was almost 7 years ago when deep learning was very hot and everybody was using deep learning. We thought, okay, so maybe we could use these models to get much better predictions for a particular process. We tried that. We tried many variants of deep learning, and we were surprised to find that simple logistic regression performed as well as deep learning, right? So I would, in the interest of having a less complex model, you might want to just choose logistic regression if it's doing as well as a deep learning model, right? So I think if you want to automate some of these processes where you don't want any human involvement, right? Then you may want to find an algorithm, a universal algorithm that solves every type of problem out there. Then you might want to pick deep learning, right? But in other situations where simplicity is important, you might want to first try simpler algorithms and see if they perform as well as a deep learning algorithm. Right? So, yeah, I mean that's a good question. Why don't we just stick to this and ignore all of these algorithms? Now, these algorithms, each of these algorithms here, they were developed perhaps with a particular nuance in the problem, right? In the classification, regression, or clustering problems, they all have a certain strength, an area or a type of problem where they are good at, right? But if you have, and the other problem with using neural networks is you often need a lot of data, right? Significant amount of data. In engineering problems, data is expensive. Doing experiments is expensive. You cannot generate any amount of data that you need. If it's images, for instance, you can generate lots of images. There are lots of images out there. It's not expensive. I was listening to a talk by somebody at Stanford a few years ago, maybe now, where they were using machine learning tools to build models on a certain physics experiment. The experiment cost them a few $1 million every time they run, and they can only collect 10 or 12 data points per experiment, right? It's a very expensive experiment, and if you want to use deep neural networks or something like that to build a model, it's not going to be feasible, I think, because you have very limited data, and any additional data point is very, very expensive. So there are many cases where you will have to resort to using one of these tools, not necessarily use neural networks. Now, prior to deep learning, there was a lot of hesitancy in many engineering disciplines to use neural networks for a few reasons. One, they are black box models, so you don't really understand what's happening inside. And two, they are data hungry. You have to provide a lot of data. And perhaps there's another reason. Neural networks prove to be very inefficient in generalization of data. Right? So you collect some data and then you build your model. But if you go outside the operating region in which you've collected your data, neural networks often did not perform well. Yeah. Right. Right. Oh yeah, it's okay. So what you're saying, I see what you're saying. The statement I'm making is specifically for neural networks, because other algorithms have special structures in them, and they work well with problems that have those features that are relevant to that particular algorithm. So let me make it a bit more clear. So let's say you're doing least squares, linear least squares, right? If the underlying model is linear, and you know that, then you're going to get a really good model using linear least squares. Now, you can also use a neural network on the same linear process, but it's going to be very messy, because neural networks, you use activation functions, which are nonlinear. Now you're trying to approximate a linear function with a nonlinear neural network. You might need a lot of data. It's still not going to be as good as your original linear model, because you know that the underlying system is linear. You were able to use a linear model. So, that's an example where it's very obvious that you wouldn't want to use a neural network. And in fact, you'll probably find that despite giving it a lot of data, it will not perform as well as a linear model, right? If the underlying system itself is linear. So that is, those are the lists that you see here are what I would call statistical learning approaches. And a lot of these algorithms were developed in the 80s, in the 90s, and into the 2000s, right? And I would call them classical machine learning algorithms. And all of them involve, or a majority of them involve some form of optimization in them. So you formulate a problem, for instance, take support vector machines, it's actually an optimization problem. We'll get to that in a few days. And it's true with other algorithms as well. K-means, it's not an optimization. I mean, there is some form of optimization in many of these methods. Okay. All right. Any other questions? Yeah. Okay. Right. I mean, that's a good question. In the morning, I talked about informativeness of data, right? Yeah. Is there a metric? Is there a way to check if you have informative data? I don't know, and I don't think it's possible for every data set. The best way to check it is to test your data, the model on a test data set, right? You've probably heard of training, testing, and validation, right? So we'll talk about that in the next lecture. There's a formal way of checking if your model is good. Does it have the generalization properties? Okay, but unfortunately, there's no good answer to your question. I mean, how can I tell if the data that I have is good enough to generalize? One thumb rule is if what you want to predict or the data corresponding to it are not in your training data set, then your model is probably not going to predict that, right? So as an example, say you trained your data on images of dogs, and then you feed it a cat, you can't expect your model to say that it's a cat, right? So because it's not in the data set. So you have to be careful and make sure your data are rich enough and include all kinds of things in it so that when you provide it with a new data point, new image, it can use sort of its memory and tell you what it is, right? Sometimes when we say intelligence, I think it sort of evokes certain images of something that is supernatural. But in artificial intelligence, in machine learning, intelligence is basically a model with certain parameters and some mathematical operations in it, right? That's all there is to it. And those parameters in your model capture the essence of the data in some form, and that is, that information, that memory, which is captured in the form of model parameters, is used on new data to reveal what that new data are. Now, if your new data are not in the original data set and your model has never seen that or anything similar to that, you're likely to get predictions that are wrong, right? So that, so your data have to be rich in that sense. They have to have all sorts of things. Have you heard of data imbalance? No? Okay. So a few years ago, we were trying to work with an industrial company. They had a classification problem. I think it was a pharmaceutical company where they manufacture vaccines for polio. And manufacturing these vaccines is like cooking, right? It's a batch process. You have some sort of a reactor. You put all the ingredients in it. You close it. You add a few other things. You wait for the process to conclude in 10 to 14 days. Okay? And then you remove your product out of it. That's the vaccine, or some form of vaccine. And every time they do this, they get a certain quality of vaccine. And they notice that sometimes, even though they're repeating the same thing, the quality of vaccine is bad, and then they have to throw away the entire batch. They can't use it. They're very strict about the quality of the drugs, vaccines they're making, right? Now, we had a lot of data from this process. Out of, let's say, 50 times they made this vaccine, maybe 3 or 4 times they had to throw it away because the quality of vaccine was not up to the standard, right? So now you have 2 classes of data. One class where everything went well with the process. Another class where things did not go well, right? So roughly, let's say, 97% of the data are from the normal process where everything went well. 3% of the data is from abnormal process where something went wrong. Okay. Now, if I ask you to build a model, a classification model that tells me, given a data set, whether it's a normal data set or an abnormal data set, what would you do? I mean, just intuitively, right? I want it to have very high accuracy. You don't have to build a model in your brain. That's hard. But right. Right. Yeah, so, I mean, this is sort of exactly what one of my students did. He came to me running and he said, oh, now I have a model that predicts with 97% accuracy that whether a batch is good or bad, right? So a simple model could be, you always say your batch is good, right? You're going to be correct 97% of the time, but that's not useful. You really want to find those batches that are abnormal, right? That's where the real value is. And the reason that if you just use this data to build a classification model, you end up with that type of model is because there is what is called class imbalance. Abnormal data set constitute only 3% of your data, and the normal data set are 97% of your data, right? So when you have such heavy class imbalance, you have to be careful when you build these classification models. Did I answer your question, I think? Okay, yeah. Yeah. So, I mean, I think that's more or less what is normally done. So when you have such huge imbalance between classes, you throw away some good data, reduce that so that there's some semblance of balance between the 2 classes, and then you build the model. Right? Yeah. Otherwise, you can always say it's a good batch, and you're going to be correct 97% of the time, and it's a good model, right? But that's not really what you're looking for. You want to identify the other class, the abnormal class. Oops, sorry, I think that's my phone. I borrowed a phone from my dad, and I don't know how to use it. I don't know how to silence it. All right. Okay, so the first group of algorithms or class of algorithms that I talked about are statistical machine learning algorithms. And those algorithms have been developed over the last 3, 4, maybe 5 decades, right? They've been around for a very long time, although we were not calling them machine learning algorithms, including least squares. Right? So that's the first major breakthrough in statistical machine learning. Some support vector machines and a few other algorithms that I listed there. They're a bit more recent. Least squares, of course, is very old, but SVM and a few other algorithms are a bit more recent. They came about in 1990s and early 2000s, et cetera. The second major breakthrough, I talked about this briefly earlier this morning, is deep neural networks. Right? I had a plot. Yeah, I want to start with this, and I'll go back to. Maybe I should just go in the order in which my slides appear here. Okay, so the second breakthrough is deep neural networks. Deep neural networks. Do you want to take a break? 5 minutes? Or? 3:40, right? Or 3:30? 3:40, yeah. So neural networks, deep neural networks are not new. This is a plot from Ian Goodfellow's book. They existed for nearly 80 years in one form or the other. They used to call them cybernetics, connectionism, neural networks, etc. The popularity, this graph here shows the frequency of the word or the phrase cybernetics, connectionism, neural networks are used over many decades. So they're all very similar, but right now we use the word neural networks to describe this particular type of machine learning model. And we are able to do deep learning or build these neural networks with a lot more layers right now because of the growing data sets. And you'll see here that in the 1900s, there were some data sets that were available for building models. This criminals data set that only had about 1,000 data points. And with time, you will find the proper legend for this graph in Ian Goodfellow's book. But the point that I want to illustrate here is that with time, we start generating more and more data. Right? We have enormous volumes of data right now that did not exist a century ago. Right? So you see this tremendous increase in the amount of data that is available. These are different benchmark data sets that have been released by various researchers. And as I mentioned earlier this morning, you'll find a lot of these benchmark data sets, some really cool benchmark data sets on Kaggle.com. It's also a website that's used by researchers to post benchmark problems. Right? If you have some interesting data set, you want people around the world to try using that data set to solve a certain type of machine learning problem, I believe you can post it here. Lots of people post data sets here in different disciplines for anybody to access and solve and showcase their models. I talked about this ImageNet breakthrough this morning, so I'm going to skip this slide. It's very similar. And during this time, it's not just that the data that is available to us has increased, but we've also built neural networks with more connections. Okay, so I will talk about neural networks in a bit in greater depth, but neural networks typically have these neurons. You can think of them as small mathematical functions. Those are connected in different ways. What this graph shows is the number of connections per neuron that people have used to train models. In 1960s, for instance, you had very few connections per neuron. And with time, we now have models with millions and billions of connections. Sorry, not billions, but thousands of connections with per neuron. This line here shows number of connections per neuron. In a fruit fly, it's about 100. In a mouse, 1,000. Humans are somewhere over here. We have a lot more connections per neuron. Now there are models that are approaching the average number of connections per neuron in humans. Okay, so we are able to, and that's possible because we have that computing power that I talked about this morning, GPUs and all that stuff. We have the computing power to have more connections per neuron. That's why we're able to do that. And to go with that, we also have these larger data sets. This graph here shows the number of neurons in models. That again, sorry, I don't have the legend for these numbers. Each of these numbers represents a well-known model in the literature. Okay, but the point that I would like to highlight is that over the years, the number of neurons in these models have also increased quite dramatically. So humans have 10 to the power of 11 neurons in them. So this cluster over here, this is right now this is a bit old, almost 10 years old, shows some of the larger models that humans have built with that many number of neurons, 1 million neurons. And I suspect LLMs have a lot more neurons than what you're seeing here in this picture. So what are deep neural networks? I'm going to do a very high-level introduction to deep neural networks. Later in the workshop, one of our colleagues from University of Alberta is going to talk about deep neural networks in much more depth. So the idea behind neural networks comes from how our brains work and the neurons in them, the connections in those neurons. A single neuron in a neural network is essentially a mathematical function. So let's say you have 3 inputs to a neuron. You find a linear combination of those 3 inputs. In this case, U1, U2, U3 are your inputs. Linear combination of those is W1, U1, W2, U2, plus W3, U3. W1, W2, and W3 are some weights that you have to calculate, you have to estimate. U1, U2, U3 are inputs that you know, right? This is the data that you have. And then you pass this linear combination of inputs through what is called an activation function. An activation function is essentially a scalar function, a scalar nonlinear function. There are many different types of activation functions that are used in designing these neurons. For instance, sigmoidal functions, hyperbolic tangent functions, and a very popular activation function called rectified linear units. Now, a sigmoidal function looks like this. Okay, so that's a sigmoidal function. It's an activation function. So basically, if your input is in this region, then it's going to be 0. If your input is over here, it's going to be 1. So that's a sigmoidal function. You can have different types of activation functions like that, and that's one single neuron. Okay, that's how you build one neuron. Then what you can do is arrange these neurons in different layers. This is layer 1. This is layer 2, layer 3, and so on. So you can put these neurons together in layers and add many layers to form a neural network. Okay. And you can have different connections between neurons in adjacent layers. The first layer is called the input layer, and then you have several hidden layers. There is typically an output layer. Now, once you have this structure, this is what is called an artificial neural network. Once you have this structure, you don't know what these weights W1, W2, and W3 are, right? So for each neuron, you will have many weights associated with them. Each neuron will have different weights depending on the number of connections that neuron has, number of inputs that neuron has. And typically, when you design these neural networks, you pick your activation function a priori. You're not searching for the optimal activation function. Instead, you just pick one and stick with it, right? So let's say we pick a sigmoid activation function, and the only unknowns in the neural network now are these weights, W1, W2, W3, or the weights for each of these neurons. Okay. So if you have, say, 100 neurons, and each neuron has 3 inputs, then you're looking at 300 weights, right? It's a really massive, I probably shouldn't say massive, given large language models have trillions of parameters in them. But it's a large optimization problem, right? Now you can think of adding more layers, more neurons in each layer. This can very quickly become a very massive optimization problem. Once you set up your neural network, you have to find those weights, and you find those weights through training. Okay? You estimate the weights by solving an optimization problem. Okay, that's called training a model. You set up your neurons, set up all of those activation functions, and then formulate an optimization problem to find the weights. Okay, so that's what is called training a model. Okay, so when you train a model, you're finding those weights. And it turns out that optimizing or finding the weights is not very straightforward because of the complex structure of the neural networks. That's where people like Jeffrey Hinton and others have come up with an idea called backpropagation, which is used in solving the corresponding training-related optimization problem. Now, once you train your model, you have all the weights, right? So all the weights on the neurons are known. Then you want to use the model for inference or for prediction. Then all you have to do is provide it the inputs. The weights are all there. You just have to calculate the linear combination with respect to the weights for each of those neurons, pass it through the activation function, generate an output, and then you move on to the next layer and so on. Okay. So that's called prediction or inference, where you use the weights and inputs to estimate the outputs. Yeah, I briefly talked about this. I'm sorry, some of these fonts are not showing up properly here. You minimize, in order to train a neural network, you minimize some sort of an objective function and error objective function with respect to each weight. And this minimization is performed using gradient descent, gradients of this objective function, or estimated using chain rule. And that's what is called backpropagation. The vanilla artificial neural networks, the one that I showed you earlier, are difficult to deal with when you have temporal data, meaning time series data. If you have a static function, say for images and so on, they're good, but if you have time series data, they're not necessarily good because they lack memory. Time series data often have a memory associated with them. They have a fixed architecture, fixed inputs and fixed outputs. So this is what you see at the top is a simple artificial neural network, and you can sort of in the picture at the bottom, I'm representing each layer with a color-coded rectangular box. Okay, so it's the same thing. This is a simple artificial neural network, and this is also what is called a one-to-one recurrent neural network. So what are deep neural networks? Deep neural networks are essentially artificial neural networks with more than 3 layers. In the previous slide, I showed you a one-to-one recurrent neural network. Now you can imagine putting all those neural networks together in a sequence, as shown here. On the y-axis, I'm showing the depth of the neural network. On the x-axis, I have time. And when you have multiple layers in a neural network, it allows for learning representations, which I talked about earlier, that are otherwise not possible. Sorry. Okay, so I'll just wrap it up in 3 minutes, and then we can go. So you know, when you have these multiple layers, you have what is called a many-to-many recurrent neural networks. That's a deep neural network. They enable complex learning complex concepts from much simpler concepts. So when you have multiple layers, I have another example where I'll show what it means as in the image classification problems. Okay, so it's right here. Yeah. No, the vanilla artificial neural networks with the one that I showed you earlier. They're not very good at building models for temporal data, time series data. Recurrent neural networks they represent time series data much better. Yeah. So if you have time series data, you don't want to use this structure. You want to use this type of a structure. Your recurrent neural network. Yeah. Right. Yeah. Yeah. Great question. I often wondered, how are people coming up with these different structures? You'll be more surprised. Yeah, so you'll be more surprised when you see a convolutional neural network, right? Or long short-term memory, LSTM neural networks. They're all they are used for time series modeling. Not convolutional neural networks, but LSTMs and recurrent neural networks. How did somebody come up with these ideas? I think there was a lot of trial and error, right? These are not ideas that came about in an afternoon, somebody thinking about it and generating these ideas, right? They actually tried many different things, many different structures through experience and the learnings from those experiences. People have fine-tuned these structures. So a good example is convolutional neural networks. Have you seen convolutional neural networks, the structure? It seems very weird that somebody would come up with a structure like that, right? But the person who came up with this structure was giving, or somebody closely related to somebody from University of Toronto, who was at least tangentially associated with developing convolutional neural networks. He gave a talk at my university, and I asked him, so how did you come up with this structure? It just seems quite arbitrary, right? And the response was, we did not come up with this in one day, right? It took many, many years of fine-tuning. We ran into problems and errors with different types of images. And then those errors helped us develop some intuition into what we need in the networks. And that's how we came up with these different structures, right? If you think about large language models, they have a very unique structure. The neural networks that are used in large language models have a unique structure. It's called transformers, right? So what is the intuition? It depends on the problem. So in this case, in recurrent neural networks, in the picture that you see here, the intuition there is when you have time series data, there is perhaps a static model underneath that is repeated again and again. So it's an example. So if you have an engineering system, a dynamic system, you can write it as follows: plus some noise, yt equal to g xt ut plus some noise. Okay, so this function is not changing. A lot of time series data are generated by, this is called a state space model. Okay, and if you have your time series data xt and yt, and you try to build a neural network to predict yt from all of these xt, you will not, off-the-shelf neural network will not do a good job because this state space model has memory in it that your feed-forward artificial neural network will not be able to capture. But what we do there in recurrent neural networks, the intuition is as follows. So you build a neural network for this f and g, and then you sort of unfold it in time, right? So for each of these layers that you see here, this one represents f and g, those functions using neural networks, and at different times you have you're using the same functions f and g but different inputs. You know, when x is 1, the input. So let me try to draw the same picture here, but differently. So f and g. So I have a neural network that approximates these two functions, f and g, and my input to this is x0. Input to this is x0, and the output from this is y0. Okay? This is a neural network. This is the standard feed-forward neural network that I showed you in the previous slide. Now I can use the same network, the same f and g functions, but now this f receives x1, and this g receives x1, and it spits out y1. Okay. Again, this is a standard feed-forward neural network. Now, when you put all of these neural networks together, then you have your recurrent neural networks, and that's the intuition behind recurrent neural network. And you can perhaps provide similar intuition to different types of neural networks, including large language models and so on, convolutional neural networks. Euler method. To update the weights. I'm sure there are lots of optimization methods. Gradient descent is the most popular method. You can imagine these large neural networks have hundreds of thousands or maybe millions of parameters. So there are efficient ways of using gradient descent methods. For instance, stochastic gradient method is a very popular method for training neural networks with millions of data points. Does it answer your questions? Okay. All right, we can pause here. There's more that I'm going to cover tomorrow. All right, thank you. Appreciate it. Yeah.
We'll have a tea right now.